right, so here we're continuing with section 1.2. We saw in the last part that basically to figure out the domain, you need to see what x's are allowed to be plugged into the function. What values will give you a real number as output. An added part to that is that if your function is an application problem or part of an application problem, the domain has to make sense. This example is intended to illustrate that. In this function, we've got f of x, which is equal to 3x squared, a nice simple polynomial function. There's no division, so there's no risk of division by 0. There's no square roots, so it appears everything's fine. You could square any number you want, so the domain is all real numbers. Okay, so that's fine. So now, suppose that I told you that I have this other function. We're going to call it a of r, and it will be pi times r squared. I'm using an r for the dummy variable instead of an x because the meaning for it is that this function, sorry, it's not a good circle, this function will tell us the area of a circle with radius r. And the thing is that circles have to have a positive radius. You can't have a circle with a negative radius. If r is 0, you have a point and not a circle. So here, although we're just squaring, there's no division by 0 or anything unusual happening, our domain for this is going to be the set of r such that r is greater than 0. Just because our function a is basically an applied function, not just a general function that doesn't have a context or story to it. So in short, if you're working with an application problem of some sort, you need to make it so that the domain makes sense. All right, so here are a couple of functions that we can try. So you should pause the video at this point and try on your own to find each of these domains. You can find them in both interval notation and set builder notation. In the first one, 8, we have 3 times the square root of x minus 2. And so if we're taking a square root, the input or radicand has to be greater than or equal to 0. So if that's going to happen, x has to be at least 2. Okay, so we've expressed that both in set builder and interval notation. In 11, this one is interesting because it does have a square root, but the input to the square root, that x squared plus 4, is always positive, right? X squared is always greater than or equal to 0. And so x squared plus 4, in fact, has to be always greater than or equal to 4. If this fits your background, I mean, this isn't necessary to answer the question, but if this fits your background, you could think about how the graph of the parabola y equals x squared plus 4 would look like this, right? It is always greater than or equal to 0. The graph is entirely above the x-axis. So for this one, x can be anything, the set of all x such that x is a real number or negative infinity to infinity. In number 14, we see that the one thing we have to worry about is the fact that there's a division, so there's a potential for division by 0. We can't have x being 6, right? Because if x is 6, then 6 minus 6 will be 0, causing us to divide by 0. So we've simply excluded 6, so the set of all x such that x is not 6, and then negative infinity up to 6, union 6 to infinity. Here the round parentheses again mean that we're excluding the 6. In 17, this one took a little more care because we need to factor that denominator. If you need help with that factoring, let me know. That would be part of intermediate algebra, but I can help you with that if you need. So factored that. The numerator, it doesn't really matter, right? X could be 3, that's fine. The numerator on a fraction can be 0, that's fine. But x can't be negative 11 and x can't be 2. Right, so in set builder notation, the set of all x such that x is not equal to negative 11 and x is not equal to 2. For interval notation, it's a little trickier. What might help you would be to draw out a little hunk of the number line. So, and then we're going to punch some holes in it, okay? So here's the whole number line. It extends from negative infinity up to plus infinity. Okay, but we've seen that we can't have x be negative 11, so we'll punch a little hole in it right there, throw away the negative 11, and we'll also throw away the 2. So what's left? So everything that's left will be from negative infinity up to, but not including the 11, from negative 11 up to 2, and then from 2 up to positive infinity. So there's 3 pieces or intervals that we have to hook together to make the complete answer for this one. All right, in number 20, we've seen one like this already. Here we have 5 over the square root of x minus 3. The numerator doesn't matter here. The denominator, we need the radical to be okay, and we also need to make sure we're not dividing by 0. In order to make it so we're not dividing by 0, x cannot be 3. In order to make it so that we're just taking the square root of a non-negative number, x has to, in fact, be greater than 3. So that's what we have down here, 3 to infinity, or the set of all x such that x is greater than 3. Number 23 is pretty interesting because there's a lot going on in it. We have the square root of x minus 6 on top of the square root of x minus 4. So there's a division and 2 separate square roots that we need to consider. So let me start with the things that I know that x cannot be. So I know that x cannot be 4, right? Taking a look at it, I can see, okay, if we had 4 for x, we'd have the square root of 0 in the denominator. We can't have that. So that's true. And then for the square root of x minus 6, we need to have x be greater than or equal to 6, okay? For the square root in the denominator, the square root of x minus 4, we need x to be at least 4 for the square root part. We've already established with the division that we can't have x being 4. So let's think about how that's going to play out. So we have our whole number line from negative infinity to positive infinity. We've seen that x cannot be 4. Okay, so let's punch a little hole in it. And then we've seen that, okay, well, x has to be greater than or equal to 4 for the radical, so we're going to throw away everything smaller than 4. In fact, the numerator radical is even more picky. It's not sufficient to be just greater than 4. We need to actually be greater than 6. So greater than or equal to 6. So we'll take all of the numbers that are less than or equal to 6 and discard those. So the overall domain is the set of all x such that x is greater than or equal to 6, or just simply the interval from 6 to infinity. So looking at the original function, it looked like that was going to be a lot more work than it was. But fortunately, it turned out just to be this relatively simple description. In the last several examples, we saw how to find the domain from a formula for a function. In the next couple of examples, we'll take a look at how to find the domain and range from a graph of a function. So recall that the domain is the input to a function. The range is the output to a function. For our graphs, the x would make up the domain, and the y values would make up the range. So for this example shown, the part that you're seeing here in blue, that's the graph. The way I think of the domain is what part of the x-axis would get covered up if you smash the whole graph up against the x-axis, which is where the domain values lie. So if you smash that whole graph against the x-axis, what part would turn blue? It would be everything from -5 up to, and it's included, right, because it's got a solid dot there. It would be from everything from -5 up to, but not including 5. I'm showing this as not including 5 because the graph continues kind of to get closer and closer to 5, but it doesn't look like it ever reaches it. We'll look at graphs that behave more like that later on, but for now, that's what we've got. For the range, I would think about, well, that's the y values. What if we smash the whole graph against the y-axis? If we smash the whole graph against the y-axis, what part's going to turn blue? So the y values would be from negative infinity up to and including 5. That would be the range. Remember, always when you're looking for domain, you're looking for inputs. For range, you're looking at outputs. Okay, so let's try 3 of these. So here we want the domain and range. You'll want to pause this and try it on your own and then see how we do. All right, so for this first one, 28, we want the domain. For simplicity, I'm just going to use interval notation for these. For this, for the x values, it looks like they run from 4 to 8, including the 4, because there's a dot at the left end, which says that the function is defined to be 10 or be 8 at 4. And then at the other end, 8, there's a hollow circle. So it will go up to and not include 8. For the range, we want to think about the y values here. So the y values will extend beginning at 2 and going up to and including 8. Okay, make sure that you can see that. Okay, for 32, for the domain, what are the possible x's? This one has a fixed start. The left end looks like it's at -3. And the right end goes up to, but doesn't include the 2. So I'll put a round parenthesis there. For the range, now we're looking for y values. This will go from -5 up to 4. Okay, last one. Here, the domain begins at -4. We're looking at x's. And at this time, the x values will go up forever and ever. Notice that unlike the last example, there is a arrow on the right side indicating that it keeps going. So this will go from -4 up to infinity. For the range, it looks like we have y values that begin at -2 and just keep going up forever and ever. As you look at the graph, it looks like it continues to rise a little bit. So it looks like as x increases, the y will increase also. So the focus of this few examples was to see how to find the domain and range using a graph. Prior to that, we found the domain using a formula. We didn't really look at all at how to find the range using a formula, in case you were concerned that you missed it. Okay, but that will, we're not quite finished with section 1.2. We'll just have one more part for that.